Okay, so in this introductory video, I'm going to show some YouTube clips that demonstrate a very, very important wave interference phenomenon called resonance. So these 3 or 4 demonstrations is a way of visualizing it before we get into the notes. Notes aren't particularly lengthy. There's no new equations here. It's just an understanding of this phenomenon. Resonance occurs at all aspects of nature. In fact, much of what we understand about nature down to the smallest level is really resonant events. Okay, so again, the key big idea is it's an interference. It's a special case of interference where essentially waves meet in such a way where the timing is just right that they amplify. Things get louder, they get brighter, they get bigger in size without having a large input of energy, but rather have a series of small inputs of energy. Okay, so the first one is a fairly simple one. It's something we're all familiar with, and that's pushing of the swing. So let me start the video clip and show how resonance applies to pushing somebody on a string. So you can hear they're demonstrating that if you push with a frequency, so let me just pause this, just make sure we're clear what we have. So resonance is all about timing. So you have to understand that there's 2 frequencies that we have to be aware of, okay? So in this case, we have a frequency of the kid on the swing. In other words, a swing is a pendulum, and a pendulum swings with a frequency, a natural frequency. And hopefully remember that that frequency, which is related to period, depends on the length of the pendulum, not how much mass is on there. So this child, no matter how far he swings, no matter how much mass is, they're going to have a particular frequency. The second frequency that matters for resonance is called a forced frequency. It's coming from an external input, in this case from the father, I'm assuming the father, from this person. He is going to apply a force on a child at a given interval, a given frequency. So in the beginning of the demonstration, okay, so let me back up a little bit on this again, right? He is pushing with a frequency that doesn't match the frequency at which the swing goes, so the kid doesn't really go anywhere. Now you can see he's timing his pushes such that the frequency of his push exactly matches or pretty closely matches that of the swing. And so what's happening is he's giving small inputs of energy, and what's going on is that the kid is swinging higher and higher. In other words, if you look at that pendulum as a wave in a sense, the amplitude is getting greater and greater. Okay, so that's really all what the resonance is about. And like I said earlier, it's everywhere in nature. So let me show you another classic example. Some of you asked about this before. Okay. So let me make sure we can get this framed correctly. All right, well, it's not perfectly framed. All right, so here's the noise. Let me pause a second. So off to the side, there is a speaker, okay, playing, it's kind of focused, playing a loud sound, and that sound, the waves are hitting this crystal, this glass crystal, okay? And they have it under super slow-mo. So you can see the vibrations of the glass itself. You notice that those amplitudes of vibrations are fairly large. Okay, normally if you just tap a glass and you hear a sound, that means the glass is vibrating, but the amplitude is on the order of fractions of a millimeter, let's say. It's microscopic. Here you see a macroscopic amplitude on the order of millimeters. Okay, so we have a large amplitude, which means a large energy. So why does this speaker giving it a lot of amplitude? Well, you might think because it's so loud that it's making it vibrate with a great energy, but it doesn't work like that. What's going on is the speaker is playing at the right frequency. It's at, let's say, 900 hertz. So the 900 hertz waves are coming and hitting this, and the glass, because it's glass, because of its shape and how much water is in there, in this case it isn't getting water, it has what is called the natural frequency, similar to the swing in the other example. So the idea is we can get the energy of vibrations of the glass to amplify. That's constructive interference, right? That's the wave interference. If the frequency of the sound coming in matches the frequency that this would normally vibrate. So the time it's just like pushing on a swing. So as the waves come in, they push, give a little energy. Then just as this comes back, it hits it again at the right time, gives a little more energy, and we get a resonance. And the resonance happens very quickly. Don't worry about the loudest thing. It can shatter the glass if it's too big. So there we see a speaker breaking glass. So you naturally ask, well, how about an opera singer, right? You may have heard of an opera singer shattering glass if they hit the right frequency. It's not so much how loud they sing. That is important, but that's not critical. So here is another clip. Okay, so notice he's trying to hit a frequency, hold a note. And he has a straw in there because the straw starts wiggling around if he's able to sustain that note for a long enough period of time that the glass starts vibrating greater than normal in amplitude such that it moves the straw around. So that kind of gives an indication that he's hitting the right note or close to it. So it's not the air of his breath that's moving the straw, it's the vibrations against the glass. And I want to emphasize, this only happens when you're really near or at the critical frequency. Any other frequencies, it's not going to do anything. Think back to when the guy was originally pushing a kid. If he was pushing at some random frequencies, the kid didn't essentially go anywhere. So the question is, can he sustain this long enough to actually break the glass with the human voice? And you notice he's getting tired. This requires a bit of energy.
Oh my God! It's vibrating against my lip. It hurts. All right.
All right, so it's very difficult to achieve. Give it one more try.
We do. I want to see.
All right, and based on his reaction, I don't think there's anything fake about that. His voice really did shatter the glass. Took quite a bit of tries. The conditions had to be just right. It's not easy to do. I've had people try it before. All right, the last demonstration I want to show you is a case where we definitely don't want resonance to occur, and as engineers, we have to be very cognizant. So let me set this up. So we have a helicopter, twin prop helicopter. So when the propellers go around and around and around, they send vibrations through the body of the helicopter here. Okay, so any machine, think of a washing machine, all right? And when things start turning, there sends vibrations through that. So what you want to avoid from a mechanical engineering standpoint is a resonance. You don't want the frequency at which this vibrates to match one of the natural frequency modes of frequent vibration that the body of the helicopter has because of its shape, of the material, what's in it, etc. So it's fairly complicated for structures, but in building buildings, it's critical that we understand what vibrations it naturally, what frequencies it naturally vibrates at so we can make it earthquake proof, etc. Okay, so here is going to be a case where one of the frequencies, or the frequency of the props, matches one of the natural vibrational frequencies of the helicopter. Therefore, the vibrations build up, constructively interfere, and give us resonance. And you know you have resonance when you get extra loud sound or extra large vibrations. In other words, it's an amplitude effect due to matching frequencies. So you don't want this to happen in a helicopter. Okay, it's just not good for it structurally, as you can see here. Okay, so that was a fail, and this is just a test demonstration that they have to alter the body of it somehow so that it doesn't vibrate with frequencies that overlap those of the propellers. Okay, so the tutorial will just sum up some of the key ideas here, and then I'll probably link some other examples of this.